Hello everyone, I am Karan Masru. Welcome to this video. In this video, we are going to discuss solution of the problem of the day, that is first and last occurrences of x. First of all, let us start by understanding the question. So what does question say? It says that given a sorted array ARR containing n elements with possibly duplicate elements. So the size of the array is n, it is sorted and it may contain duplicate elements as well. Okay, here there is a bit printing mistake. The task is to find the first and last occurrences of an element x in the given array. So for a particular integer x, where it is present for the first time and where it is present for the last time in the given array, we need to return those two positions. If the number x is not found in the array, then return both the indices, that is the first presence and the last presence, as -1. Let's look at example for better understanding. So suppose the size of the array is 9 and x is equals to 5. So the first occurrence of 5 is at index 2, so we were printing 2, and the last occurrence of 5 is at index 5, so we are printing 5. So output is 2, 5. Okay. If we look at the second example, the size of the array is 9 and x is equals to 7. Now 7 is present only at one position, so that would be considered as first as well as last. So that is index 6, so we will be returning 6, 6. Okay. Now suppose in this case 10 was given, then 10 is not present, so we would be returning -1, -1. Okay. We need to complete the function find that takes array integer n, that is the size of the array, and integer x, which we need to find, as parameters and returns the required answer. The expected time complexity is log n and expected auxiliary space is constant, and the constraints are given here. Now if we look at this problem, basically we want to find the first and last occurrence of an element x in the given array. The array is sorted, so what we can do, we can apply binary search. So to find the first occurrence, we can apply a binary search, and to find the last occurrence, we can apply a binary search. So we need to apply two binary searches, which will result nothing but what? In a time complexity of log n, which is basically given here. So since the array is sorted, we can take this advantage. So we will do two binary search, to first to find the first occurrence and second to find the last occurrence, and return their indices. In case they are not present, we will return -1, -1. So this is the concept. Now let's look at its actual implementation. So if we talk about the actual implementation, so what I have done is I have taken two integers left and right, which will basically store the first occurrence and the last occurrence of x in the given array. I have taken one vector answer because we need to return the answer in vector form. First I have done binary search left, that is to find the first occurrence of x in the array, and I have stored the result in left variable. The starting index would be 0 and the ending index would be n-1 initially, because we are considering the whole array in the binary search. We will pass array, the size of the array, and the element which we want to find, x. Similarly, we will in right we will store the last occurrence of x in the array, and we will call another function, that is binary search right, to find the last occurrence of x, and we will pass the same arguments, and then we will push the answers left and right in our answer vector and return the answer. Now let's look at binary search left and binary search right. So now if we look at the binary search left part, which basically returns the first occurrence of x in our given array, then suppose this is our given array and x is equals to 2. Initially L would be 0 and h would be 7, as there are 8 elements. So first of all, m, that is the midpoint, that is what we do in binary search. For the part we are considering in the array, we'll compare the middlemost element with our given value which we want, and then depending upon that we'll traverse on the left side or the right side further. Okay, so m would be what? L plus h by 2, that is 7 by 2, that is nothing but 3. So my m would be pointing to here. Now if array of m is equals to x, here it is equal to x, but let's look at further other conditions. If array of m is less than x, so it is less than the required value, then we will go on the right hand side. Suppose my required value x was 6. Now the value at this point is 2, so we will do binary search on the right hand side part. So what I'll do, binary search left, I'll call this function only, but now my L will become m plus 1, because the first parameter is L and second is h, and h will remain as it is. So I'll do binary search on the right hand side part, and other parameters will remain the same. So this is for equal to, this is for less than, and this is the case when array of m is greater than x. So suppose my x was 1 and my m was here, so now I need to do binary search on the left hand side part. So binary search left, I will call the same function, but now I'll do on the left hand side part. So from L to m-1 and then the same parameters. Okay, this much is clear. Now there are also duplicates in the array. So if array of m is equals to x, if it is equal to x, but is it the first occurrence, we need to check that also. So if L is equals to m, so basically Suppose I am only L is equals to H, I am only looking at one element in the array. Okay, I have reached that part of the binary search. So this will also be equal to M. Now there is no part on the left to be considered, because at each step we remove the half part of the array. Suppose initially our array was of 8 length, then it became 4 length, then it became 2 length, and then there is only one element left. Suppose now if this is equal to X and if L is equals to M, there is no left hand side part remaining to check. So this would definitely be our answer, so we will return answer. But if there is a left hand part, it means that L is less than M. So if the left hand side is also equal to X, in this case here X is equals to 2, M is equals to 3. So array of M is equal to 2 is equal to X. But is it the first occurrence? How we will know? If the element before that is also equal to X, yes, it is equal to X. So this is not our answer, and we will do binary search on the left hand side part, because we want to find the first occurrence. So we will do return binary search left from L, M minus 1 array and X. But in case that is not equal to X, so suppose this was 1 and 1, so this is not equal to X, this is less than X. So this is definitely our first occurrence. So in that case we would return M. So I hope all these conditions are understood. Now let's understand binary search right. So now binary search right is almost the same as binary search left. So what we are doing is we are taking the starting and the ending index of the part of the array which we are considering, calculating the middle part. If that value is less than X, we want to find the last occurrence of X. So if that value of mth index is less than X, then we will do binary search on the right hand side part. So from M plus 1 to H. Here it is equal to, here it is less than. So when will it go in else part? When it is greater than. So if array of M is greater than X, then we will do binary search on the left part. So but the function will be binary search right. Remember, binary search left is to find the first occurrence, binary search right is to find the last occurrence. So here we will do binary search on the left remaining part, but we will call this function only. Okay, don't get confused. And the parameters would be from L to M minus 1, because array of M is greater than X, right? Now if it is equal to X, what we need to find is, suppose X is equals to 2 and we are having 2 to 2 and this is our M and this is our H. So if it is equal to X, then is it the last occurrence? We want to find that. So if H is equals to M, it means that if the higher index is equal to the mid index, it means that this is the last element, we cannot go further, then we will return M. But if array of M plus 1 is equals to X, array of M plus 1 is equals to X, yes, so this is not the last occurrence, we will remove it and we will do binary search on the right hand side part. So from M plus 1 to H. And else means there is elements on the right hand side, but it is not equal to X. So suppose 2, 3, 4, this is my array, this is my M, this is my H, and X is equals to 2. So array of M is equals to X, yes. Is H equal to M? No. Is array of M plus 1 equals to X? No, this is greater than X. So this is the last occurrence. There might be 2 present before, but this is the last occurrence, because on the right hand side of this I do not have X. I have value greater than X. So in that case I'll return M. Okay. What would be the time complexity? We are doing 2 binary searches, one for the first occurrence and one for the last occurrence. So it would be log n. And what would be the auxiliary space? If we look at the auxiliary space, then we are taking only a few variables, left variable, right variable. We are taking a vector answer, but in that also we are storing only 2 variables, so that would be constant. But because we are calling binary search, the stack size which stores the recursive functions can go up to log n. So in this case the time complexity would be log n. But you can also do this in big O of 1, that is constant time. How? Here we have called the binary search recursively. You can do it iteratively. You can make a while loop. While L is less than equal to H, M is equals to L plus H by 2, and the same process. So it will not occupy the space in the stack for recursion. And in that case, you will get big O of 1's auxiliary space when you will do iterative binary search. Okay. Now let's submit this code. So we have solved this question successfully. I hope you have understood the solution completely. Thank you.